All right. There we go. Hello, everyone. Wow, this is probably the most questions just right off the bat that we've had so far. That's awesome. So why don't we just get right into it? Our first question is from Tuyen, and he states, draw a molecular orbital diagram of beryllium 2 that has a plus charge, and we're going to compare this to another beryllium 2 with a negative charge. Now it's going to state calculate the bond order for each molecule, determine if it's paramagnetic or diamagnetic, explain why or why not. You expect these ions to be stable. Okay, so let's go ahead and just start off with drawing this. Now, the main thing to focus on for like the very beginning, any single time you're drawing these molecular orbital diagrams, is you have to know your electron configuration of beryllium. So I'm going to start off with just writing the electron configuration, just looking at my periodic table. And then what I'm going to do is just kind of write this out. So this would have been 1s2 and then 2s2. So that is all we have for electron configuration of beryllium. Now, this is going to play into effect because those electrons are going to help us determine where they're going on the atomic orbitals, all right? Like whether the s orbitals, which is all we have in this case. So now what I'm going to do is I'm just going to draw out your typical molecular orbital diagram of just Be2. And then from there, I'll start doing the plus and the minus. Okay, so drawing this out, what we're going to start off with is we're always going to show, here, let me make this better. We're always going to show our energy that's increasing. And then you want to start off with the lowest orbital that you have, which in our case is the 1s orbital. So this would have been known as our bonding 1s orbital. And then here, this would have been our antibonding 1s orbital. And then this would have just been 1s, just drawing this out to show you how this is going to look. And this is really important to know. And then here, this would have been sigma as well, 2s. This is 2s, 2s. And then pretty much what we're going to do is just draw everything out according to like raising or increasing energy with our orbitals. So that's why 1s is on the bottom and 2s is on top. Now what I'm going to do next is, since beryllium is going to be on either side, and then in the center, that's where we combine both of these beryllium atoms together. Well, we know that there are two, so we know there are 2 electrons in each s orbital. So what I'm going to do is I'm going to take that into account. And then I'm just going to focus on the left side for right now, and I'll show you what we'll do. So I'm going to add 1 and 2 electrons for that s orbital, and then I'm going to continue on the opposite side since it is the exact same beryllium atom. And then from here, what we're going to do is you're always going to add up the like outside atoms or electrons, and then that's what we combine together to put in the middle. So then in the middle, we have a total of 4 electrons to work with. So this is going to be 1, 2, 3, and 4. So that's complete. And then I'm going to keep going. And then now for our 2s orbital, we're going to see that we have 1, 2, and then same on the other side. So we have once again 4 to work with in the center. So it's essentially what you're doing is you're counting the outer electrons and then combining them to like fill that middle. All right, so you're just adding them together. Now, this was just your typical uncharged Be2. So what I'm going to do now is I'm going to include that plus charge. And whenever you're including a plus charge, that means you're actually removing electrons. So since it's just a +1 charge, we will remove 1 electron. Now, what I have to also indicate or show is that one of these berylliums atoms has that positive charge. So since we said it has to eliminate an electron, I'm actually going to remove an electron from the highest or the last place that it filled. And then so that means that removes it from here. Okay, so now that we see that, I'm going to identify, is this paramagnetic, diamagnetic? What's our bond order? So whenever we're looking at paramagnetic versus diamagnetic, well, paramagnetic means that we're going to have some we're not going to have pairs, essentially, is that. So like diamagnetic, everything is paired. We have paired electrons. So in this case, this would have actually have been diamagnetic, actually paramagnetic, just because we have that unpaired electron on top. So this is paramagnetic. And then from this point, I'm going to identify our bond order. So the formula for our bond order, so BO or bond order, that's going to be our bonding electrons minus our anti-bonding electrons. Bonding electrons all divided by 2. And I'll show you how to do that. All right. So I'm going to go back and look at all of the molecular orbitals in the center. And then here we'll see, okay, well, anything without that little star or asterisk is going to be our bonding orbital. Everything that has that little star or asterisk is going to be anti-bonding. So then in this case, I'm just going to count the bonding. So this is 2 and 4. So we have 4 bonding electrons minus our anti-bonding, which would have been here. So 2 and then 3. So that would have been 3 divided by 2. This gives us 1/2. So for our first one with the plus charge, that's going to give us a bond order of 1/2. Now, anything that is pretty much think of it as the higher the bond order is, the more stable it is. So this is actually really weak. Anything that is 0 is completely unstable. And then in this case, since this is really 0.5, it's not too stable. So now let's see if the negative 1 or the negative charge is going to be better. So let me go back to just what this used to look like. And I always like to just draw out the actual template, like just doing the neutral compound. And then what I'm going to do now is if I were to, let's say, put a negative charge here, okay, this would continue. And then what would happen is that if we're adding an electron, that means that, okay, well, and actually, there we go. If I'm adding 1 electron because it's negative, then I have to put, once again, that negative charge on one of these atoms. And then that means I'm actually adding an electron. Now, it's a little bit interesting. That was a negative. Yeah, it was a negative charge. Okay, so in this case, it would have continued. Like, think of it this way. If this was a negative charge, then that actually means I would have continued and had, and this is actually interesting that they're doing this, but it would have been 2p1, and then this molecular orbital diagram would have continued. And let me erase this. But this would have continued, and we would have had, here, let me see if I can, there it is. This would have continued, and I would have had our 2p orbitals on either side. Just placing 1 because we're only looking at 1 extra electron. And then in the center would have been our pi, our sigma. All right, I know this is a little bit a longer question. And then this would have been our antibonding pi bond, and then orbital, and then this would have been our sigma antibonding. All right, so then we only have 1 electron to work with, so that would have been on top here. Okay, so that being said, this is still going to be paramagnetic just because it's an unpaired electron, right? We have this unpaired electron on top. The last thing to do here is to figure out how many, what's our bond order, is it strong or whatnot. So I'm going to start off with our bonding electrons, and then our bonding electrons, let's recount those. So our bonding electrons are 2, 4, and 5. So we would have had 5 bonding, and then our anti-bonding would have been 2 and just 4. And then once again, that actually would have given us the exact same thing. So then right there, it actually would have had the exact same bond order. Explain why or why not you would expect these ions to be stable. It's not too stable just because it is 0.5 bond order. The higher the bond order, the more stable it is. So that's what I would state for this one. All right, hope that makes more sense. I'm going to move on to another question. Okay. And then for everybody who's new, because I'm seeing some different names, welcome. Thank you so much for being here. I'm Melissa Maribel, and if you want to know a little bit of who I am a chemistry tutor. I've been doing this for quite some time. I have my bachelor's degree in chemistry, so I definitely have seen a lot of chemistry in my life. So welcome. Thank you for being here. Okay. We have our next question, which is which of the following molecules have dipole moments? Okay, so it looks like we're going to talk about polarity in this next case. So indicate polarity of each bond and the direction of the net dipole moment of the molecule. And then our first part of this question, we're comparing 2 different two different types. All right, so let's just start off with drawing our Lewis structures. And then with Lewis structures, recall that for carbon, we're going to have 4 valence electrons. Oxygen has 6, but there's 2 of them, so I'll multiply by 2. So we'll have 12 plus 4, a total of 16 electrons. And then now what I'm going to do is just place carbon as our central atom and then surrounded by 2 oxygens. How I like to do this is I'm going to basically surround my outer elements with all of the lone pairs or electrons first, and then start to form double or triple bonds where we need it. So then at this point, what I'm going to do is I'm just going to add electrons, all right? And then here we would have seen that this would have been 16 if we counted everything up. And then the only difference now is the reason why this isn't stable or correct is because carbon needs to have a full octet, meaning it has to have 8 valence electrons. So I'm going to move these electrons to form a double bond. I'm also going to do the same thing on the other side. And then this would have been the correct structure, where this would have had 2 double bonds on either side. Okay. Now let's predict the polarity of this. Whenever we're looking at our overall molecule of being polar or not, we're first going to look at symmetry. So this is actually completely symmetrical because we have an oxygen on either side. And then essentially what would happen is though oxygen is very electronegative, this is going to be nonpolar because think of it as like they're both going to be pulling the opposite direction with an equal amount of force. So there is no pull of electrons or dipole moment that occurs. That's why it's nonpolar. Now let's look at the next one. And then let's go back to drawing this. So N2, or nitrogen, would have had 5. There's 2 of them, so multiply that by 2. Then I'm going to add this to 6. So this would have been a total of 16 electrons again. And then at this point, let's go ahead and put oxygen in the center. And then we'll see that actually this would have been surrounded here, just so I can get to as many questions as possible. But this would have been how the structure would look like after we would have written this out. This one actually wants to be in this sort of order, where nitrogen and nitrogen are bonded to each other, then nitrogen and oxygen. So in this case, the one that's going to be the best is going to actually be something that has a triple bond. And the reason for this, we would have to go into a lot of formal charges and like actually be able to see the formal charges of every single one, where if we were to do the formal charges, this would have had a -1 charge, and this would have had a +1 charge. Your most electronegative atom, which is oxygen, wants to have a negative charge if it can. Okay, so if it's part of the formal charges. So that's why this would have been correct. Now, what I'm looking at here is when we're looking at polarity, once again, we're looking at whether this is symmetrical. So this is not, because we have nitrogen and oxygen. Those are different atoms overall. So our overall electronegativity is going to be, like, the most electronegative atom is going to be oxygen. So this would be polar, just for the fact that it's not symmetrical, and then our dipole moment would be between that nitrogen and oxygen. Where is it going to pull? Towards the most electronegative atom, which is oxygen. So that would be for that first part. For the next one, since we have multiple ones, we'll just draw the structure. So this is PH3, HN3, and ASH3. Okay, so for the first one, phosphorus would have had 5 valence electrons, and then hydrogen 1 really times 3, so a total of 8. And then I'm going to have this surrounded by hydrogens. And then we'll double check, do we have enough electrons? We do not. We need 2 more on that central atom. So any single time we have lone pairs on our central atom, that makes it polar. So this would be polar. And where this dipole would go is towards phosphorus. Okay, so that's where our dipole moment would be. And then now we'll look at our next one. So this is HNN3. And then the one that this would favor, and because this would be 1 electron plus 5 times 3, so actually 16 electrons. And then here, it's a little bit different just because of that nitrogen. So remember, hydrogen cannot be your central atom since it only has 1 valence electron. It could only make 1 bond. So I'm going to write this out with all 3 nitrogens and then the hydrogen at the end. And then when we look at this, you're actually going to have something like, You could have a triple bond and then everything else be a single bond. That's one possible answer. Another one that I have seen, and actually I would say this one would be favorable, but I have seen another type that is also favorable. Here. There we go. So either one of those. Now, is this going to be polar? I would state, and even just looking at it, because there is no symmetry, right? It's not completely symmetrical. I would state that this is slightly polar, just for the fact that hydrogen is not electronegative whatsoever. And then really this kind of pool would have been here, just because we're looking for that difference of pool of electrons or electronegativity. So it would have been towards that nitrogen. Okay, that would have been our dipole moment. And then lastly, arsenic, so ASH3, and then arsenic is going to be 5 valence electrons. This is once again going to be 3. We'll have 8. Arsenic would have been in the center, surrounded by 3 different hydrogens. And once again, we're going to see, okay, we actually have those lone pairs. So this will be polar just because of those lone pairs. And then it's always going to favor going in that direction of the most electronegative atom. All right, so that was that one. I'm going to move on to Jose's question. Okay, so Jose has, let's see, I'm going to just jump to like right where it asks the question. So we're given a balanced equation. Let me write that out for you guys. And it looks like this is a bit of gas laws. So anyone who's struggling with gas laws and ideal gas laws specifically, it states how many grams of sodium azide are needed to produce sufficient N2 gas to fill a 45 times 45 times 25 centimeter bag to a pressure. So what I just wrote out is your volume. Anytime it gives you, well, 1 centimeters, and 2, whenever it's giving you like that this is actually going to be cubic centimeters, that's your hint that this would be volume. And then we'll have to find that in a second. It also gives you your pressure is 1.20 atmospheres and a temperature. All right, so we're given a temperature of 15 degrees Celsius that we will have to convert. So the first thing that I'm going to do is I'm just going to make sure that all the units are in the correct unit. So I want volume to be in liters. We also want temperature to be in Kelvin. Pressure is fine. It is in atmospheres. The reason why I'm doing this is because our gas constant for the ideal gas law has to be, or it is 0.0821, and the units would be liters atmospheres divided by moles Kelvin. It's just the easier one to do. There are several different gas constants, but that is, I'd say, the most common that I've seen on exams. And then now what I'm going to do is I'm just going to multiply all of these together to find that volume. So multiplying 45 times 45 times 25 would give us a very large number, but this would have been this value. And then this is cubic centimeters. What I'm going to do now is I'm going to convert this to liters. And then there was one thing that we had to know, that 1 milliliter is equal to 1 cubic centimeter, because we're going from cubic centimeter to milliliters, then to liters. All right, so that's exactly what I'm going to do. Multiplying this really just by this conversion factor. I know it's just going to be 1, but just showing the work. And then at this point, I'm going to convert this to liters. So this would have been 1,000 milliliters is equal to 1 liter. And then really we're just dividing this by 1,000. So it's like I'm just moving this decimal place over 1, 2, and 3 due to the 3 zeros on the 1,000. Then this would have been 50.625 liters. All right, next I'm going to change the temperature to Kelvin. So just changing this to Kelvin, I'll add 273. And then we'll see what that gives us. So 273 plus 15. And then our new converted temperature is 288 Kelvin. Okay, so this question is asking for grams. Our first step, and actually after doing all these units, we're going to plug this into the ideal gas law and solve for the amount of moles, or N. And then one little thing with this as well is sufficient N2. How many grams of that? Yeah, I'll get back to that portion, but I'm just going to figure out how many moles we have. So using PV equals nRT, I'm going to manipulate this formula, so like move it around just so we can solve for N. And then when I do that, I'm dividing over RT. So this cancels. And then our formula that we're just going to plug everything in is going to be as such. And now I'm just going to plug in all the values that we had. So N is equal to, our pressure was 1.20 atmospheres, and then on top would have been 50.625 liters. On the bottom would have been 0.0821 liters, atmospheres, moles, Kelvin. And then our new temperature was at 288 Kelvin. Okay, so all of this, all of our units would pretty much end up canceling, and we would be left with just moles, which works out perfectly. Now multiplying the top, 1.20 times 50.625, all divided by these two multiplied by each other. So let's do that portion. Okay, and our moles are now 2.569 moles. Okay. And then I'm going to go back to the question and just see to make sure which moles, for which compound this is. So we're asked to find how many grams of sodium azide are needed to produce a sufficient amount of N2 gas to fill that amount of volume to a pressure of 1.20 at 15 degrees Celsius. And I'm hoping, so needed to produce sufficient N2 to fill. Okay, so this is pretty much telling me that we're trying to produce this. It actually doesn't tell us of which one. During a sudden crash, got it. Okay, so in the beginning of the question, there it was, where it's saying during a crash or sudden stop by the rapid generation of N2 from sodium azide, these moles that we just found are actually going to be that of N2. So always kind of beware of that, just because we will have to do a little bit of stoichiometry. That's pretty much the reason why they give us the balanced equation. So what I'm going to do now is I'm going to do a mole to mole ratio. Going back to our balanced equation, I want to change this to moles of sodium azide. So here. So we have 3 moles of N2 gas, and we have 2 moles of sodium azide. So that's what I'm going to use just to change my compound to the correct one that we're looking for. So this would have been, I said 3 moles of nitrogen gas, and then 2 moles of sodium azide. And then the last step here is to figure out the molar mass of sodium azide and then multiply by it so we can convert this to grams, and then we're finally done. All right, it's a 3. So let's figure out what our molar mass is. Sodium has a molar mass of 22.99. Nitrogen has a molar mass of 14.01, but there's 3 of them, so I'll multiply by 3, and then I'll add everything up. So let's see, 14.01 times 3 plus 22.99. This would give us 65.02 grams of sodium azide, and then there's 1 mole on the bottom. Okay. So our moles and moles of N2 would cancel, moles of sodium azide would cancel. We're left with grams of sodium azide. Multiply everything straight across. So 65.02 times 2 times that 2.569, all divided by 3. And then we'll double check our sig figs, of course. So this is pretty much the answer that I get. I'm going to go back to the question and see how many sig figs we had. So with sig figs, our smallest amount of sig figs was only 2. So I'm pretty much going to change this into scientific notation to make sure that we only have 2 sig figs. So changing this, I'm going to move this over 1 and 2. So this is 1.1 times 10 to the second grams of sodium azide. All right, so that would be our answer for that one. And then now I'm going to move on to Luna's question. All right. Okay, so I'm going to need my, here, just grabbing the formula. I know you're talking about unit cells now. Okay, just grabbing my formula for those. So for unit cells, there are specific types, and of course, this one is specifically telling us it's a face-centered cubic unit cell, so that's going to help us a lot. Now, we're given a metal crystallizes with a face-centered cubic lattice. The edge of the unit cell is, okay, so we know our edge length, which is symbolized as L, is 408 picometers. Calculate the number of atoms in the unit cell and the diameter of the metal atom. And then for that, our edge is equal to our, yes, it is. Okay. And this froze on me. Okay. There we go. Sorry about that, guys. This froze on me. Okay. So I said the length was equal to that amount. And then with this formula, I'm just going to make this a tiny bit different. I've also seen it, just in case you might have seen this in books or whatnot. I've also seen this formula as L is equal to 2R rad 2, just because the square root of 8 is actually 2 rad 2. So that's kind of another way to write it. Now, what I'm going to do next is, because they're asking for the diameter, I first have to find the radius. And the nice thing is, since we have our L, or our edge length, we'll have to plug it in. All right, so I'm going to plug that in. Picometers, and then I believe there's one little thing that I wanted to mention. Where is it? Yeah. Where is it? Typically, you're actually going to see your radius. It's going to be in centimeters. So even before plugging that in, let me just convert this to centimeters. It's just a common thing to note. However, do we have our density? No, we don't. Just saying if we have our density, and we don't. Okay, I don't even see why you would bother even changing it to cubic centimeters. Come to think of it, I think you're fine. Since we're just looking for our diameter, I'm going to go from there. So I'm just plugging in this value in for R. All right, and then from this point, I'll plug everything in and then just solve for R. So I'll divide over that radical 8 and solve at this point. So R is going to equal, and let's actually do that math. 408 divided by the square root of 8. That gives us 144.2 picometers. Next, since we're looking for the diameter, we know that we just have to multiply the radius by 2 to give us our diameter. So we'll multiply this by 2. So our diameter is equal to 288.5 picometers. So that's our diameter. Next, we're also asked to figure out the number of atoms. All right, so this is going to be for a FCC, or face-centered cubic unit cell. What we're looking at is the atoms per the cell are actually 4. So that's something to know. The fact that they told us it's a FCC also tells us that there are 4 atoms per cell. All right, so that's something to definitely know. And then that's going to help us identify or figure out how many atoms we have. Now, what we're going to do is we're pretty much going to be multiplying this by Avogadro's number, and that's pretty much it. So I'll take the 4 atoms, and then I'm going to multiply this by Avogadro's number, since we are looking for the number of atoms, not the number of moles. Let's see, in the unit cell, and the diameter of that. Interesting. That would have just been 4 then, if they were just looking for the atoms. And actually, this is per unit cell, because typically they ask for moles, but they're not in this case. Let's see if there's anything else that I can do. Yeah, typically they ask for moles or grams. In this case, I actually would have just said that it would have just been 4 atoms, since they are asking for number of atoms in the unit cell. Yep, that's it. No need to multiply by Avogadro's number, just because they're not asking for any more information. So that other part was just knowing how many atoms per cell there were, and that would be 4 for FCC. Okay. And then Amina actually just said, thanks for doing these live streams. You are very welcome. I really enjoy teaching you guys. Know that. Yeah, it's definitely awesome to see. I actually enjoy seeing all these questions. All right. Jeanette says, a compound diffuses through a porous cylinder 3.20 times faster than helium. What is the molar mass? All right. So this is going to be a specific question or a specific formula, and then it is known as the rate of effusion. And then just the fact that it states effusion, that's your hint. So our rate of effusion, what that formula is going to look like is we're going to have some sort of effusion of, let me see if I have my rate of diffusion formula, but it is going to be equal to the square root of our molar masses. There it is. So our rate of diffusion is going to be on top, and then it's typically like a diffusion of, like, let's say compound A, and then on the bottom would be the same thing, rate of diffusion of compound B, and then what we would then see, it is equal to the square root of our molar mass of compound B and our molar mass of compound A. To memorize this formula, they're always the opposite of each other. So now this is telling us to figure out the molar mass of it, so of the compound that we don't know what it is, okay? So they tell us that at least one of them is helium. All right, so we can determine, okay, well, we have helium, we can figure out the other molar mass. So let's say if compound A were helium, then I know the molar mass of helium, so I can plug that in. I don't know the molar mass of compound B, that's what we're solving for. And then this 3.20 is actually the ratio between the rate of diffusion A and rate of diffusion B, meaning it's this entire portion, okay? So a ratio really is just talking about some sort of fraction. So this would have been equal to 3.20. And then from this point, I'm going to actually plug in the molar mass of helium, which would have been 4. And then all we have to do at this point is solve for the molar mass of B. So the first thing is to get rid of that square root by squaring both sides. That cancels out the square root. And then let's actually square this value. 3.20 squared would have given us 10.24, and that's equal to our MB, or molar mass, of 4. I'm going to multiply over that 4 to both sides to cancel, and then that would be our answer. So the molar mass of our, this is molar mass, not molarity. Molar mass is then equal to 40.96. Since it is molar mass, it's grams per mole. All right, so that would have been our final answer. And then I am going to answer one question per person just to make sure that everybody can at least have one of their questions answered. So I'm going to move on to Amanda's question. And if an ice cream company, yum, needed to make 150 kilograms of ice cream, so let's see what we're given already. We're given 150 kilograms of ice cream. How much energy would be lost cooling it from 35 degrees Celsius to 0 degrees Celsius? Okay, so since we're asked how much energy, this should be your hint or your clue that we're probably looking for Q. Okay, so how much energy would be lost cooling it, meaning we're looking for Q, so our formula for this would be this. Now, they should have given you, thank you, perfect, okay. Was it still the ice cream? Because I'm going to need the specific heat capacity. I believe it is. What mass of your ice cream mixture at, sorry, there's so many questions, I'm still looking for it. There it is. Of a metal having, does it give you your specific heat capacity, Amanda, for the ice cream question? Because I think these are two different questions. I'll see what I can do with that, but it would have to give you your specific heat capacity. I'm going to keep going with it and see what I can do with this question. But this would have been Q. And then what I want to do now is our mass is going to be in grams, so I'm just going to convert that. So this is 150 kilograms, and I'm going to convert this just to grams. So 1 kilogram is equal to 1,000 grams. So multiplying this together, we'll get a very large value. So this would have been 150. I'm just going to add on 3 zeros, 1, 2, 3. And so I'm going to change this to scientific notation just so it's not so large. So 1, 2, 3, 4, 5. This is 1.5 times 10 to the 5th grams. And that's what I'm going to plug in for our mass. And I might just leave this set up just because I do need the specific heat capacity of ice cream, as strange as that sounds. 0.92. Perfect. Thank you. So the specific heat capacity is 0.92, and your units are typically joules per grams Celsius. And in this case, I'm going to plug that in because we did need that. Next, I have to figure out the change in temperature. So they gave us that our initial was 35 and our final was 0. So subtracting those two values, 0 minus 35 would still give us a negative 35. It is important to know that it would have been negative, especially because this question also tells us that it's giving off, or I believe it said it was giving off, or let's see. Oh, how much energy would be lost? Yes, so that was the key word, lost. So that makes it negative. And then so our Q would be negative, and we'll multiply everything together, and we'll be left with joules. So 1.5 to the 5th, 10 to the 5th, and then times 0.92 times negative 35. And then our final answer, which I'm going to convert to scientific notation, this would have been joules. It's joules because our grams and grams cancel and our Celsius and Celsius cancel. We're left with joules. And then let me just convert this. So this would have been 1, 2, 3, 4, 5, 6. So negative 4.83 times 10 to the 6 joules. That is the energy lost. All right, next question. Let me just follow where the next question was. Stevie. Okay. A calorimeter, the equilibrium temperature of copper and water is determined in an experiment, but the water was replaced with a mixture at the same initial temperature as water. What would happen to the equilibrium temperature? Sorry, I'm going to read that again. Calorimeter, the equilibrium temperature of copper and water is determined, and then the experiment was run again, but the water was replaced with a mixture of at the same initial temperature as water. What would happen to the equilibrium temperature? So we're changing the temperature. Give me 1 sec to understand this question. So we had some sort of copper combining with water, and the water was replaced at the same initial temperature as water. I don't really see what happened. I don't really, I'm trying to understand your question, Stevie. I'm sorry. I don't necessarily see why that would change the equilibrium temperature if the same initial temperature was the exact same. Equilibrium would shift if we increased or decreased the temperature. So I would expect no change given that. Oh, I skipped this question. I'm sorry. Oh, I did. Oh, I'm going to go back to your question. Sorry about that, Kasra. Yes, I'm going to your question now. I'm sorry about that. There it is. Okay. 5 identical 1 liter flasks contain here. And then, by the way, Stevie, there would be no change. Okay. Just letting you know, I don't see that there would be a change since we're not changing the temperature of equilibrium. Okay. So let me read the next question. Castro states 5 identical 1 liter flasks contain the following gases at 25 degrees Celsius, and our pressure is 1 atmosphere. For which gas do the molecules have the smallest average kinetic energy? Okay, so I'm going to need some more formulas for this. So let me go back. All right. And we're given helium. We're given, this is a multiple choice question. Okay. C, NH2, and then D, all of the gases are the same, which is what I'm leaning to. All, okay. And then which of the gases for which gas do the molecules have the smallest average kinetic energy? So this has to do with our kinetic molecular theory. So if everything is the same, like our temperature is the same, our volume, our pressure, what I predict from this is the fact that, like, some people might have thought, okay, it's going to be the one that has the smallest molar mass. Now, typically what I see is for kinetic energy, remember that kinetic energy is the energy of motion. So all of these are still going to be moving, essentially. Now, this is a bit of a trick question. You're not going to see that it's any of them. It's actually going to be part D, where all of the gases are the same, just because since we have all of the same temperatures, all of the same pressures and whatnot, the kinetic molecular theory then states that, yes, it's going to be all of the gases. All right, so all of the gases are the same for that one. Next question, Lisa, I'm going back to yours. I don't know why it skipped it, guys. Sorry about that. I'm trying to follow like along each one. Pretty much whenever someone asks a new question, it completely like shifts down, and I'm trying my best. Sorry about that, guys. Lisa, okay. This is a structural formula. So we're looking for meta-dibromobenzene. Okay, so drawing this out, first I'm just going to start off with the benzene ring. So our benzene ring, we're going to have something like this. There we go. And then from there, we're going to see this is dibromo. So dibromo tells us there are two bromines. And then next, I'm going to just put one in the top location. And the next part here is going to be placing the next bromine in the meta position. So the meta position would have been right here. Just kind of going over real quick, whenever you have some sort of benzene ring, and let's say some sort of halogen, which I'm going to label as X, and let's say you want to place this in either your your ortho position. This would have been ortho and ortho. This would have been meta and meta, and this would have been para. So that's kind of something to note. That's how you would typically, see these types of questions to help you out. You always start with some sort of halogen or something already attached to that ring, and then from there, this M or P or O would tell you where to put that next bromine or whatever halogen we're attaching. Okay. Now let's see the next question. I'm just looking at through the line. I believe Brittany. Brittany is our next question. Yes, making sure not to skip anybody. What is the formal charge of CHF3? Okay, let's start off with drawing our structures. So our valence electrons here would have been 4 for carbon, just 1 for hydrogen, and then we have 3 fluorines. Fluorine has valence electrons of 7, and then this is times 3. So we have 4 plus 1 plus 21. So this would have given us 22 plus 4, giving us 26. And then now I'm just going to draw this out. So carbon is going to be your central atom, and then this would have been surrounded by fluorine, fluorine, 3 fluorines, and 1 hydrogen. And then now I'm just going to double check that we have the correct amount of valence electrons. So far we have 2, 4, 6, and 8. I'm going to add lone pairs. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Yep, that checks out. So looking at what are the formal charges. What is the formal charge of this? So I'm going to look at the formal charge of every single individual element. So I'll start off with the central atom, and then your formal charges, or FC, is going to be equal to the valence electrons of whatever we're looking for, like in this case, carbon. And then that would be minus the sum of our bonding electrons plus our individual lone pairs, or really just individual electrons, okay? We might have also stated this as non-bonding electrons. Non-bonding electrons are those electrons floating around, or the lone pairs, okay? So if I'm looking at just the formal charge of the central atom, which is carbon, our valence electrons typically for carbon are 4. Then I'm going to go back and see what are our bonding electrons. So specifically, I'm just looking at the electrons that are directly bonded or directly touching that carbon. So in this case, the ones in pink just show that there are 4 directly bonded or touching that carbon. So we have 4 bonding electrons plus individual electrons. Well, there's none. We don't have any lone pairs on our carbon, so 0 for individual electrons or non-bonding electrons. This would give us a formal charge of 0 because this is 4 minus 4. So far, our central atom has a 0 formal charge. Now I'm going to move on to, we can do fluorine. And then since all of the fluorines are essentially the same, right, we only have a single bond, I only have to do one fluorine and it's going to have the exact same formal charge. So fluorine has a valence electron of 7, and then here this is going to be minus the amount of bonding. So let's look at the ones directly bonded to fluorine. Directly bonded to fluorine is just 1. And then how many individual lone pairs or really electrons surrounding it do we have? We have 1, 2, 3, 4, 5, and 6. Okay. All right. And then here I'm going to state that we had only 1 that was bonding, and then we had 6 for our individual like floating around electrons. So this would have been 7 minus 7, so this is 0. So all of these fluorines have a formal charge of 0. And then next for hydrogen, we'll do the same exact thing. And then this would have been for hydrogen. So hydrogen only has 1 valence electron minus how many bonding? Well, we know it's going to be 1 just because we only have 1 directly bonded to it. And then there are no valence electrons, or not valence electrons, lone pairs. So this is 1 plus 0, so 1 minus 1 would also give us 0. So all of our formal charges are 0. It works out perfectly, and this is actually a great way to check yourself to see, is the structure stable? Anytime you have like your central atom is 0 and then everything else is either 0 or your most electronegative atom is negative, then it tells you it's a good structure. Okay, so everything's 0 for this one. All right, I'm going to move on to another question. Okay, what else we got? Tarika asks, can you go over bond enthalpy equations and oxidation numbers? So I typically do more like specified questions. So for now, I'm going to pick one of those just because they are general topics and I can be here for days explaining this. Okay, so I'm going to pick possibly, let me know which one you want me to pick, but I can do bond enthalpy equations. I believe you're talking about Hess's law. So I can do Hess's law. Let me see if I can, I don't think I have anything pulled up there, but here. For, let's say Hess's law. I need an example real quick. Let me actually see if no, I don't. Darn. Okay. I was hoping I have something already ready, but I don't. Let me grab my Hess's law thing. Just because I need an example. Where is it? 1 second, guys. Just looking for it. Let me see if I have it. Just want to actually show an example. There it is. Okay, so let's say for Hess's law, we were looking at this equation. Let me write them out and then I'll show you talking about it. So this is, let's say we're asked to find our change in enthalpy. And actually, let me see if I could actually upload it, guys. Just looking at what I have. I think this could actually work. Just so I don't waste time writing this all out for you guys. Yeah. Let me see if this works before I can do anything else. 1 sec, guys. I might just take a screenshot. Okay. One thing that I will say, because this is thermochemistry, if you guys are struggling with thermochemistry, I do have a replay link in the chat that I just put. So if you guys, want to better understand thermochemistry, whether it be calorimetry, Hess's law, bond energy, and just enthalpy in general, then I do recommend clicking out that link, clicking that link and seeing, rewatching the replay, because I did do a tutoring session on it for 90 minutes. So I'm going to go back to this and let me see if I can insert it, just because these take quite some time. Image, there it is. Almost there. There we go. All right. Power of technology. Okay. There we go. Perfect. Okay. This is going to be easier to actually do. Let's say you're given this. So you're calculating your change in enthalpy using Hess's law. So for this case, you're going to be given some sort of goal. And they're not going to necessarily state that it's a goal, but they're going to give you basically an equation that doesn't have a change in enthalpy, and you're asked to find it. So that's the one that is your goal. Okay. So what we're going to do first, and how we approach this question, is I'm going to look at the first reactant. And essentially what we're doing is we're trying to manipulate those 3 given equations to look like our goal or the top equation. So what I'm going to do is, for that 5, I'm going to find where is carbon. Well, here in that first reaction, there's carbon on the reactant side, so check, that's correct. Now, the next thing is we want 5 of them. So we don't have enough. We need to multiply this entire equation by 5. When we do that, we also multiply by that same exact number to our enthalpy change. Next, I'm going to keep going. And we have 6 H2s. It is on the reactant side, so that's fine. But we need 6 of them, so I'm going to multiply this entirely by 6. And then next, for our product here, we want that C5H12 to be on the product side. It's not. So what we're going to do is we're going to flip this reaction. Whenever you flip the reaction, you multiply your enthalpy change by a -1. Essentially, you're just changing the sign. So now I'm going to apply all of this, all right? So I'm going to rewrite everything, add up all the equations, and then at the end, add up our enthalpy change, and that's our answer. All right, so then now I'm going to distribute that 5. This would have been 5 carbons plus 5 O2 gases, and that gives us 5 CO2 gases. And then next, I'll distribute that 6. So this is 6 H2s, and then plus, beware of this, so this is 6 times a half. Note that 6 times 1/2 is essentially 6 divided by 2, which gives us 3. So this would have been 3 O2s. Then this makes it 6 H2Os, and that's a liquid. And then next, I'm going to flip the reaction. So my new reactants are our previous products. Just writing this all out. And then now this is on the correct side. Okay, plus 8 O2s. Next step is to combine or add up all of our reactants on one side and all of our products on the other. Okay, so that's exactly what I'm going to do. So adding everything together, this is 5 CS carbon, 5 O2s. I'm actually going to avoid the states just because there are no changes in states here. So then this is 6 H2s, 3 O2s, plus 5 CO2s, and 6 waters. Okay. That was just the reactants. Now this is going to be set equal to 5 CO2s, 6 waters. I'm going to run out of room, but this is plus C5H12 plus 8 O2s. Next step is to cancel out what you can. So we have, where is it? 6 waters. So I'm going to cancel those 5 CO2s. And then note that we have 5 plus 3 O2s, so 8. So I'm going to cancel those out. And then we're left with our goal that we wanted initially. So that's how you know you did it correctly. And then now I'm going to go back to our enthalpy changes and actually do the math. So I'll, okay, there we go. Let me not erase that. So this is going to give us, if we multiply those two values, 5 times negative 393.5, this would give us negative 1,967.5. This one would give us 6 times negative 285.8. Let me see. This is what our new value would be, just multiplying all of our enthalpy changes. This is now a positive. And then we would add all of these new enthalpy changes together, and then we'll see what we get from that. So what we would get from this point would be our change in enthalpy is equal to negative 146.3 kilojoules, right? So that's exactly how you do Hess's law. And of course, if you guys need some more help, because I do see a lot of thermochemistry questions, I highly, highly recommend checking out the link that I put in the chat, and I'm putting it again if you didn't see it. It's basically me teaching for an entire 90 minutes, actually, all these different topics, whether it be enthalpy stoichiometry, Hess's law, calorimetry, all the different calorimetry questions that I have possibly seen. Same with internal energy. So if you guys want some help with that to prep for your test, I highly, highly recommend it. I know it's helped a lot of students already. Okay, so let's see if I can answer maybe one more question. Okay. Yes. So, Juliana, I'm going to answer your question now. So, consider 500 milliliters of a 0.30 molar solution of copper sulfate solution. How many moles? So, how many moles of solute are present? Okay. This is of solution. Moles of solute is what we're finding. So all we're going to do is we first have to change our milliliters to liters. So that's exactly what I'm going to start off with. So just converting these 500 milliliters, I'm going to multiply this by 1 liter is equal to 1,000 milliliters. So really this is going to move this over 1, 2, 3. And then our liters would be 0.500 liters of, this is specifically of our solution. So this is of our copper sulfate solution, okay? So then now what I'm going to do next is recall that molarity, capital M, is actually equal to the moles of our solute divided by the liters of our solution. And this is just a way to abbreviate it, solution. Okay, so all I have to do at this point is taking my volume that I just converted to liters, and since this is the copper sulfate solution, I'm going to multiply this by the molarity that they gave us initially to get our moles. So how I'm going to separate this molarity here. Whenever you see that capital M, this is actually referring to moles over liters. So I'm going to separate this out to 0.30 moles of copper sulfate, because that's actually our solute, and then dividing this by 1 liter of our copper sulfate solution. And then that's what I'm going to put on top here. So 0.30 moles of copper sulfate, and on the bottom 1 liter of copper sulfate solution. Then our copper sulfate solution will cancel, and then we're just left with the moles. So we'll multiply at this point. So 0.5 times 0.3, and then we will get 0.15 moles of just our solute, which is copper sulfate. Okay, that would be our answer. All right, guys. Wow, questions keep coming. Thank you so much for being here and just for asking your questions. Seriously, this is amazing. This is probably the most questions I've seen so far, which is awesome. I will be doing this again next Sunday. So I do this every single Sunday for an hour. I spend time with you guys answering as many questions as possible. It is so if you definitely want to get your questions answered, I highly recommend being here when I first start the live Q&A, which is at 12 p.m. Pacific time. Now, another thing that I wanted to mention is I know we're getting closer and closer to 10,000 subscribers. I think we're at like 8,700 right now or something like that. So something that I wanted to do for you guys, and once we get to 10,000 subscribers, I'm still doing that 8-hour live Q&A. So if you guys help me get there, whether or not you share it with your friends or, classmates, anyone that can really benefit from these types, or even teachers and professors, anyone that can really benefit from chemistry help, then please share my videos. Please share my channel so we can get to that 10,000 subscriber goal and I can do an 8-hour live Q&A. All right. And then, like I mentioned, if you guys haven't checked out that link for the thermochemistry replay, it's in the chat already. So definitely check that out to help you out with thermochemistry. All right, guys, I will put that again in the description. I just put it in the chat right now. I just did that. You're welcome. I'm seeing so many thank you so muches. You are so welcome, guys. I really love doing this. All right, guys, I will hope to see you again next Sunday at the same time for our weekly Q&A. Have a great Sunday. See you guys.